First, let me to explain about the software-defined access fabric, underlay, and overlay. Cisco software-defined access, or SDA, creates an entirely new way to build campus LANs. SDA uses the software-defined architectural model with a controller and various APIs, or application programming interfaces. It still uses a physical network with switches and routers, cables, and various endpoints. At the center sits the digital network architecture, or DNA center controller, with human users making use of a graphical user interface, or GUI, and automating using APIs. In short, DNA center is the controller for SDA networks. Alright, now let me to explain about the underlay, overlay, and also fabric in the software-defined access. It is so important for us to understand the fundamentals correctly. About the underlay, here you can see the underlay, and here you can see with more detail. Okay, the network of devices and connections like the cables and wireless to provide IP connectivity to all nodes in the fabric, with the goal to support the dynamic discovery of all SDA devices and endpoints as part of the process to create overlay VXLAN tunnels. You will learn that in this underlay we will have some tunnels with VXLAN technology. I will explain it, but for now let me to say that in underlay we can have multiple devices, physical devices like the switch or routers, in most cases switches, okay, and also some connections like the wired connections, wireless connections, and also finally we will have IP connectivity to all nodes in the fabric. Okay, with this IP connectivity we can establish the overlay tunnels. Okay, about the overlay, here you can see the overlay. Look at here, this is switch 1, switch 2, and here we have some other switches, but in the overlay, as you can see, we have only switch 1 and switch 2. Between these two we have VXLAN tunnel. What does it mean? About the overlay, the mechanisms to create VXLAN tunnels between SDA or software-defined access switches, which are then used to transport traffic from one fabric endpoint to another over the fabric. Actually, we will have overlay network over the underlay network. What is the fabric? The combination of overlay and underlay, which together provide all features to deliver data across the network with the desired features and attributes, we say fabric. Okay, actually combination of underlay and overlay is our fabric. Here you can see that we have the underlay. In underlay we have some devices, some connections. Over this underlay we will have overlay. Okay, and the combination of underlay and overlay is our fabric. And don't forget, here also we have a controller, DNA center controller, that we can use it for configuration, management, troubleshooting, and also some other functions over the SD access or over the fabric. Actually, the underlay exists as multi-layer switches and they link with IP connectivity, but for a special purpose. The underlay supports some new concept with the tunneling method called VXLAN. Traffic sent by the endpoint devices flows through VXLAN tunnels in the overlay, a completely different process than traditional LAN switching and also IP routing. For instance, think about the idea of sending packet from host on the left of a network over SDA to host on the right. For instance, imagine a packet enters on the left side of the physical network, as you can see here, and eventually exits the campus out switch 2, okay, on the far right. This underlay network looks like a more traditional network drawing with several devices and links. Okay, the overlay drawing at the top of the this figure shows only two switches called fabric edge nodes. This is the first fabric edge node and this is the second fabric edge node, because they happen to be at the edge of the SDA fabric with the tunnel labeled VXLAN connecting the two. Both concept, underlay and overlay, together create the SDA, for example, fabric. I will explain with more detail about the underlay underlay and overlay, but about the controller. Architecturally, the southbound side of the controller contains the fabric, underlay, and overlay. Here we have southbound interface. By design, in SDN implementation, most of the interesting new capabilities occur on the northbound side, which are, for example, connected to the users, to the graphical user interface, to the application programming interfaces. Okay, but now we are learning first about the underlay. After that, I will explain with more detail about the overlay. About the SDA underlay, with SDA, the underlay exists to provide connectivity between the nodes in the SDA environment for the purpose of supporting VXLAN tunnels in the overlay network. To do that, the underlay includes the switches, routers, cables, and wireless links used to create the physical network. It also includes the configuration and operation of the underlay, so it can support the work of the overlay network. To build an SDA underlay network, companies have two basic choices. They can use their existing campus network and add new configuration to create an underlay network while still supporting their existing production traffic with traditional routing and switching. Alternately, the company can purchase some new switches and build the SDA network without concern for harming existing traffic and migrate endpoints to the new SDA network over time. To build SDA into an existing network, it helps to think for a moment about some typical campus network design. The larger campus site may use either a two-tier or three-tier design. It has a cluster of wireless LAN controllers, WLCs, to support a number of lightweight access points or LWAPs. Engineers have configured VLANs, VLAN trunks, IP routing protocols, ACLs, and so on, and the LAN connects to WAN router. SDA can be added into an existing campus LAN, but doing so has some risk and restrictions. First and foremost, you have to be careful not to disrupt the current network while adding the new SDA features to the network. These issues include, because of the possibility of harming the existing production configuration, DNA Center should not be used to configure the underlay if the devices are currently used in production. DNA Center will be used to configure the underlay with deployment that use all new hardware. The existing hardware must be from the SDA compatibility list, with different models supported depending on their different SDA roles. The device software levels must meet the requirement based on their roles as detailed in the same compatibility list. For instance, imagine an enterprise happen to have an existing campus network that uses SDA compatible hardware. That company might need to update the iOS versions in a few cases. Additionally, the engineers would need to configure the underlay part of the SDA devices manually rather than with DNA Center, because Cisco assumes that the existing network already supports production traffic, so they want the customer directly involved in making those changes. The SDA underlay configuration require you think about and choose the different SDA roles filled by each device before you can decide which device to use and which minimum software levels each requires. If you look for the hardware compatibility list, you will see different lists of supported hardware and software depending on the roles. These roles include, let me to explain the roles. First, Fabric Edge Node. About the Fabric Edge Node, this is a switch that connects to endpoint devices similar to traditional access switch. For example, here you can see that we have a Fabric Edge Node, or here in this figure you can see that we have, for example, some Fabric Edge Node, or other name is the for example, Edge device. Let me to write here, this is the Fabric Edge Node. Okay, here for example we have for fabric edge node. We should consider the role. After that, we can verify that our device support this role with the hardware compatibility list. Actually, this is a switch that connects to endpoint devices similar to traditional access switches. After that, we have some other devices. Fabric border node. About the fabric border node, this is a switch that connects to devices outside SDA control. For example, switch that connect to the WAN router or to an ACI application-centric infrastructure data center. Let me to show you. For example, here now we have some fabric border node. This is a fabric border node, and also we have other fabric border node. Also, we have fabric control plane, a switch that performs special control plane functions for the underlay, okay, for the LISP that I will explain it, requiring more CPU and memory, okay. This is the fabric control node here. For example, this is a switch or router that is our fabric control node, okay. Actually, we can say we should notice to the roles in the SD access. Fabric edge node, a switch that connect to endpoint devices. Fabric border node, a switch that connect to devices outside SDA control. Fabric control node, a switch that perform special control plane functions. For example, Cisco's compatibility list included many catalysts, 9300, 9400 and 9500 switches, but also some smaller catalysts, 3850 and 3650 switches as fabric edge node. Okay, for control plane or for fabric control plane control nodes, the list included more higher end catalyst switch models which typically have more CPU and RAM, plus several router models. Routers typically have much more RAM for control plane protocol storage, for instance routing protocols. The beginning of an SDA project will require you to look at the existing hardware and software to begin to decide whether the existing campus might be a good candidate to build the fabric with existing gear or to upgrade hardware when building the new campus LAN. Okay, the next option is using the new gear for the SDA underlay. You know that, as I mentioned before, we have two choices: using existing gear for the SDA underlay and using new gear for the SDA underlay. When buying new hardware for the SDA fabric that is a greenfield design, you remove many of the challenges that exist when deploying SDA on existing gear. You can simply order compatible hardware and software. Once it arrives, DNA Center can then configure all the underlay features automatically. At the same time, the usual campus LAN design decisions still need to be made. Enterprises use SDA as a better way to build and operate a campus network, but SDA is still a campus network, okay? It needs to provide access and connectivity to all type of user devices. When planning a greenfield SDA design, plan to use SDA compatible hardware, but also think about these traditional LAN design points. The number of ports needed in switches in each wiring closet, the port speeds required, the benefits of a switch stack in each wiring closet, the cable length and types of cabling already installed, the need for power, PoE, PoE plus, universal PoE, the power available in each new switch versus the PoE power requirement, link capacity, speed, and the number of links for links between switches. Okay, as far as the topology, traditional campus design does tell us how to connect devices, but SDA does not have to follow these traditional rules. To review, traditional campus layer 2 design tells us to connect each access switch to two different distribution switches, but not to other access layer switch. Okay, as you can see here, the access layer switch acts as a layer 2 switch with the VLAN limited to those three switches. As you can see here, we have access switch to distribution switch. Here we define the gateway as the IP address of the virtual IP of the hot standby router protocol. Okay, and also here we have two multi-layer switch in the distribution layer. Actually, take a moment to reflect about the traditional features we can see here. The distribution layer switch, layer 3 switch, acts as a default gateway used by hosts and often implement HSRP for better availability. The design uses more than one uplink from the access to distribution layer switch with layer 2 Ether channels to allow balancing in addition to redundancy. And STP or RSTP manages the small amount of layer 2 redundancy in the campus, preventing loop by blocking on some ports. Okay. In comparison, a greenfield SDA fabric uses a routed access layer design. Routed access layer design have been around long before SDA, but SDA make good use of the design. And it works very well for the underlay with its goal to support VXLAN tunnels in the overlay network. A routed access layer design simply means that all the LAN switches are layer 3 switches with routing enabled. So all the links between switches operate as a layer 3 links, as you can see here. With a greenfield SDA deployment, that is all new gear that you can allow to be configured by the DNA Center. DNA Center will configure the device's underlay configuration, use a routed access layer. Because DNA Center knows it can configure the switch without concern of harming a production network, it chooses the best underlay configuration to support SDA. The best configuration happens to use a design called a routed access layer design, which has these features. All switches act as layer 3 switches. The switch use the ISIS or intermediate system to intermediate system routing protocols. All links between switches, single links or Ether channels are routed layer 3 links, not layer 2 links. As a result, STP or RSTP is not needed, with the routing protocol instead choosing which link to use based on the IP routing tables. The equivalent of a traditional access layer switch, an SDA edge node, acts as the default gateway for the endpoint devices rather than distribution switches. Okay. As a result, HSRP or any first hop redundancy protocol is no longer needed. This figure repeats the same physical design that we saw before, but shows the different features with the routed access design as configured using the DNA Center. DNA Center configures the underlay with consistent setting for each instance of DNA across an enterprise. This convention simplifies operation as an enterprise completes a migration to SDA. Alright, now let me to explain about the SDA overlay. When you first think of the SDA overlay, think of this kind of sequence. First, an endpoint sends a frame that will be delivered across the SDA network. The first SDA node to receive the frame encapsulate the frame in a new message using a tunneling specification called VXLAN and forward the frame into the fabric. Once the ingress node has encapsulated the original frame in VXLAN, the other SDA nodes forward the frame based on the VXLAN tunnel detail. The last SDA node removes the VXLAN detail, leaving the original frame and forward the original frame toward the destination endpoint. Okay, this is the SDA overlay. While the summary of some of the SDAs may sound like a lot of work, all the work happens in each switch's application-specific integrated circuit or ASIC. So while it is more complex to understand, there is no performance penalty for the switch to perform the extra work. When Cisco set about to create SDA, they saw an opportunity. Making use of VXLAN tunnels opened up the possibilities for a number of new networking features that did not exist without VXLAN. Okay, because of that, SDA, actually let me to say that SDA uses LISP or locator ID or a separation protocol for endpoint discovery and location needed to create the VXLAN tunnels. VXLAN tunnels in the overlay or the data plane has many additional features. SDA actually has many additional needs beyond the simple message delivery. Need that let it provides improved function. To that end, SDA does not only route IP packet or switch Ethernet frames. Instead, it encapsulates incoming data link frame in a tunneling technology for delivery across the SDA network with these goals in mind. The VXLAN tunneling, the encapsulation and de-encapsulation must be performed by the ASIC on each switch so that there is no performance penalty. That is one reason for the SDA hardware compatibility list. The switch must have ASICs that can perform the works. The VXLAN encapsulation must supply header field that SDA needs for its features, so the tunneling protocol should be flexible and extensible while still being supported by the switch's application-specific integrated circuits. And the tunneling encapsulation need to encapsulate the entire data link frame instead of the encapsulating the IP packet. This allows SDA to support layer 2 forwarding features as well as layer 3 forwarding features. To achieve this goal, when creating SDA, Cisco choose the virtual extensible LAN or VXLAN protocol to create the tunnels used by SDA. When an SDA endpoint, for example an end user computer, sends a data link frame into an SDA edge node, the ingress edge node encapsulates the frame and send it across a VXLAN tunnel to the egress edge node. To support the VXLAN encapsulation, the underlay uses a separate IP address space as compared with the rest of the enterprise, including the endpoint devices that send data over the SDA network. The overlay tunnels use addresses from the enterprise address space. For instance, imagine an enterprise use this address space 10.0.0.0/8 for entire enterprise, okay, and 172.16.0.0/16 for SDA underlay. Okay, to make that work, first the underlay would be built using the 172.16.0.0/ for example 16, okay, IPv4 address space with all links using addresses from that address space. Okay, as you can see here, we have a small SDA design with 4 switches, each with one underlay IP address, okay, from this address space. Also, you know that the overlay tunnel creates a path between 2 fabric edge nodes in the overlay IP address space that is in the same address space used by all the endpoints in the enterprise. Okay, this figure emphasizes that point by showing the endpoint PCs on the left and right with IP addresses in the range 10.0.0.0/8, with the VXLAN overlay tunnel shown with addresses also from the same range. Alright, now let me to explain about the LISP for overlay discovery and location. This is the control plane of the SD access. You know that in SD access we use LISP for control plane and VXLAN for the data plane. For understanding the LISP functionality, ignore SDA for a moment and think about traditional layer 2 switching and layer 3 routing. How do their control plane work? In other words, how do these devices discover the possible destination in the network? Store those destinations so that the data plane has the data it needs when making a forwarding decision. To summarize, traditional layer 2 switches learn possible destination by examining the source MAC address of incoming frames, storing those MAC address as possible future destination in the switch MAC address table. When new frame arrive, the layer 2 switch data plane then attempts to match the Ethernet frame's destination MAC address to an entry in its MAC address table. This is the traditional layer 2 switching. About the traditional layer 3 routing, traditional layer 3 routers learn destination IP subnets using routing protocols, storing routes to reach each subnet in their routing tables And when new packet arrive, the layer 3 data plane attempts to match the packets or the IP packet's destination IP address to some entry in the IP routing table. Okay, nodes in the SDA network do not do these same control plane actions to support endpoint traffic. Okay, let me to explain about the component that we have in the LISP. First, fabric edge nodes. You know that SDA nodes that connect to the edge of the SDA fabric learn the location of possible endpoint using traditional means based on their MAC address, individual IP address, and by subnet, identifying each endpoint with an endpoint identifier or EID. Actually, in the LISP or in the SDA, each device has one identifier. We call it endpoint identifier. Actually, each endpoint, like a PC, has endpoint identifier. It can be MAC address, it can be IPv4 address or IPv6 address. In most cases, the IP address, means IPv4 or IPv6, is the endpoint identifier of a host. After that, the fabric edge nodes register the fact that the node can reach a given endpoint or EID into a database called the LISP map server. Actually, you know that in the for example, LISP technology, we have a LISP map server. In this map server, we have a database. This database correlate EIDs, means endpoint identifiers, to the routing locators or RLOCs. Let me to explain it. Look at here. The LISP map server keeps the list of endpoint identifiers and matching routing locators or RLOCs, which identify the fabric edge node that can reach the EID. Also, in the future, when the fabric data plane needs to forward a message, it will look for and find the destination in the LISP map server's database. Let me to explain it. Look at here. Assume that in this scenario, we have switch 3 and switch 4. Okay, switch 3 connected to one PC, and the IP address of this PC is, for example, from the range of 10.130/24. Okay, also the switch 4 connected to one other PC. For example, this is PC1, this is PC2, and here we use the range 10.1.4.0/24. Don't forget, here we are using layer 3 routing, okay, between the switch 3 and switch 4 and other switch. Actually, you know that in access layer we use the MLS. Okay, after that, the first things that should happen is advertising the range or the IP address of the PCs or the range of PCs to the map server. Look at here. With the help of some LISP message, okay, or locator ID separation protocol message, the switch tree should advertise the endpoint identifiers like the IP address, MAC address, and some other things to the map server. And here also we have other information. This is the routing locator. Routing locator related to the switch tree. It means that, for example, in this is like a router ID, okay, but it is not router ID. Here we have routing locator 172.16.3.3, okay. Now, switch tree should send this information to the LISP map server. The EID or endpoint identifier of 10.1.3.0/24 can be reachable by this RLOC or routing locator 172.16.3.3. Also, the switch 4 advertises this information to the LISP map server that 10.1.4.0/24 reachable with this routing locator. Okay, this is the separation of the location and also the, for example, endpoint identifiers. For instance, here, let me to explain it again. Switch 3 and switch 4, it just learn about different subnet external to the SDA fabric. Okay, as noted previously, switch 3 sends a message to the LISP map server registering the information about the subnet 10.1.3.0/24 and endpoint identifier with its routing locator or RLOC setting to identify itself as the node that can reach that subnet. Step 2, choose an equivalent registration process, this time for switch 4 with EID 10.1.4.0/24 and with R4's RLOOK of 172.16.4.4. Note that the table at the bottom of the figure represents the data held by the LISP map server. Okay, until now we learned about two steps of the for example LISP process. Let me to explain the next step. When new incoming frame arrive, the ingress tunnel router, this is the ingress tunnel router. Let me write here. Here we call it ITR, okay, or ingress, okay, a tunnel router. This is the router that receive, or this is a switch that receive the traffic, real traffic. We call it ingress tunnel router or ITR. Okay, when ingress tunnel router receives the traffic, the SDA node that receives the new frame from outside the SDA fabric, this is the definition of the ITR. Okay, it needs some help from the control plane to where should the ITR forward the frame. And because SDA always forward frames in the fabric over some VXLAN tunnel, what tunnel should the ITR or ingress tunnel router use when forwarding the frame? For the first time sent to a destination, the ITR has to follow a process like the following steps. Step 3. Look at here, an Ethernet frame to a new destination arrive at ingress edge node SW switch 1, and the switch does not know where to forward the packet. You know that destination IP of this packet is 10.1.3.1, the IP address of the, for example, PC1. The ingress node sends a message, as you can see here, to the LISP map server asking if the LISP server knows how to reach the IP address 10.1.3.1. You know that now here we have the mapping table learned before from the switch 3. In step 5, okay, this is the step 4, this is the 5, the LISP map server looks in its database and find the entry it built back at step 1 in the previous figure, listing switch 3's routing locator of 172.16.3.3. At step 6, the LISP map server, in most cases, the LISP map server doesn't answer directly to the switch 1, but if you want, you can configure it as a proxy to send the answer directly. But in default behavior, the LISP map server contacts switch 3's, the node listed as the RLOOK, okay, to confirm that the entry is correct. And finally, in step 7, switch 3 completes the process of informing the ingress node switch 1 that 10.1.3.1 can be reached through the switch 3. What does it mean? Look at here. We received a traffic with destination IP of 10.1.3.1. Switch 1 doesn't know how it can forward it. It will ask from the LISP map server, and after that in the database in the mapping table of the LISP map server, we have one entry for the destination 10.1.3.1 in this range, and this LISP map server knows about the routing locator that we can use it to reach to this network. Because of that, the LISP map server should redirect the request or mapping request to the switch 3, and switch 3 will answer to the switch 1 that if you want to reach or to forward the traffic to the 10.1.3.1, you can give the traffic to me. You can encapsulate the traffic with the destination IP of 172.16.3.3, and when you are encapsulating the traffic with VXLAN, okay, the traffic will be forwarded to switch 3 over the tunnel, and after the encapsulation, the traffic can be forwarded to the PC1. To complete the story, now that ingress node switch 1 knows that it can forward packets sent to endpoint 10.1.3.1 to the edge node with RLOOK of 172.16.3.3. That is switch 3. Okay, switch 1 encapsulates the original Ethernet frame and will forward it to the, for example, switch. It adds the IP, UDP, and VXLAN headers shown so it can deliver the message over the SDA network. As you can see, this is the original frame, and here we have VXLAN header, UDP header, and this IP header. In this IP header, we have source IP, the switch 1 IP address, destination IP, the RLOOK IP address of the switch 3. Actually, with that outer IP header listing a destination IP address of the RLOOK IP address, the message will arrive through the SDA fabric at switch 3. At this point, you should have a basic understanding of how the SDA fabric works. The underlay include all the switches and links along with IP connectivity as a basis for forwarding data across the fabric. The overlay adds a different level of logic with endpoint traffic flowing through VXLAN tunnels, and you know that suffice it to say that with the flexible VXLAN tunnels, SDA can encode header fields that lets SDA create new networking features, all without suffering a performance penalty, as all the VXLAN processing happens in an application-specific integrated circuits. Alright, now let me to explain about the Cisco DNA Center and also SDA Operation. Cisco DNA Center has two notable roles. First, as the controller in a network that uses Cisco software-defined access, and also as a network management platform for traditional non-SDA network devices, with an expectation that one day DNA Center may become Cisco's primary enterprise network management platform. The first role as SDA network controller gets most of the attention and is the topic of discussion in this video. SDA and DNA Center go together, work closely together, and any serious use of SDA requires the use of the DNA Center. Okay. At the same time, DNA Center can manage traditional network devices. Okay. Let me to explain about the Cisco DNA Center. Cisco DNA Center exists as a software application that Cisco delivers pre-installed on a Cisco DNA Center appliance. This software follows the same general controller architectural, for example, concept as we described before in the SDN. Actually, Cisco DNA Center include a robust northbound REST APIs, okay, along with a series of southbound APIs. For most of us, the northbound APIs matters most because as the user of SDA network, you interact with SDA using Cisco DNA Center's northbound REST API or the GUI interface. Okay, Cisco DNA Center supports several southbound APIs so that the controller can communicate with the devices it manages. You can think of these as two categories. First, protocols to support traditional networking devices, software versions like Telnet, like SSH, like SNMP, and protocols to support more recent networking devices or software versions like the netconf and also RESTconf. Cisco DNA Center needs the older protocol to be able to support the vast array of older Cisco devices and OS versions. Over time, Cisco has been adding support for netconf and RESTconf to their most current hardware and software. Alright, now let me to explain about the issues with traditional IP-based security. Imagine the life of one traditional IP ACL in an enterprise. Some requirement occurred and an engineer built the first version of an ACL with 3 access control entries or ACEs, that is access list commands, with a permit any at the end of the list. Months later, the engineer added 2 more lines to the ACL, so the ACL has the number of ACs as you can see here. Okay, the figure notes the lines added for request 1 and 2 with the circled numbers in the figure. Look at here, this is the first for example ACs, AC1, AC2 and AC3, and also we added permit, and also now after 2 months later we added AC4 and AC5. Now think about the same ACL after 4 more requirement caused change to the ACL. Actually, previously we had 2 requirements, requirement 1 and requirement 2, okay, and after some change here you can see the ACs for the requirement 2 are now at the bottom of the ACL, okay, and some ACs like the AC5, okay, apply to more than one of the implemented requirements. Some requirements like requirement number 5 required ACEs that overlap with multiple other requirements. Okay, now imagine your next job is to add more ACs for the next requirement 7, for example. Okay, however, your boss also told you to reduce the length of the ACL. Removing the ACs from that one change made last, for example, months. You remember it, right? Such tasks are problematic at best, and it means that with this scenario, no engineer could tell from looking at the ACL whether any lines in the ACL could be safely removed. You never know if an AC was useful for one requirement or for many. If a requirement was removed and you were even told which old project caused the original requirements so that you could look at your notes, you would not know if removing the ACs would harm other requirements. Most of the time, ACL management suffers with this kind of issues. ACs cannot be removed from ACLs because of the risk of causing failures to the logic for some other past requirement. New change become more and more challenging due to the length of the ACLs. Troubleshooting ACLs as a system, okay, is the next problem. Determining whether a packet would be delivered from end to end becomes an even greater challenge. Alright, now let me to explain about the SDA or software defined access security based on user groups, okay, and we can compare it with the traditional security implementation. Imagine you could instead enforce security without even thinking about IP address range and ACLs. SDA does just that, okay, with simple configuration and the capability to add and remove the security policies at will. First, for the big ideas, imagine that over time, using SDA, 6 different security requirements occurred. For each project, the engineer would define the policy with DNA Center, either with the GUI or with the Application Programming Interface API. Then, as needed, DNA Center would configure the devices in the fabric to enforce the security. Actually, you don't need to think about the IP address or some other things. You only apply the policy and automatically the policy will convert it to commands with the DNA Center, and after that it will forward to the SDA fabric. Okay, the model demonstrates the concept of intent-based networking or IBN. The engineer configures the intent or outcome desired from the network. In this case, a set of security policies. The controller communicates with the devices in the network, with the devices determining exactly what configuration and behavior are necessary to achieve those intended policies. The SDA policy model solves the configuration and operational challenges with traditional ACLs. In fact, all those real issues with managing IP ACLs on each device are no longer issues with SDA's group-based security model. For instance, the engineer can consider each new security requirement separately without analysis of an existing possibly lengthy ACL. Each new requirement can be considered without searching for all the ACLs in the likely paths between endpoints and analyzing each and every ACL. DNA Center and related software keeps the policies separate with a space to keep notes about the reason of the policy. Each policy can be removed without fear of impacting the logic of the other policies. SDA and Cisco DNA achieve this particular feature by tying security to groups of users called Scalable groups or SG, with each group assign a scalable group tag or SGT. Then the engineer configures a grid that identifies which SGTs, means which scalable group tag, can send packet to which other SGTs. For instance, the grid might include SGTs for an employee group, the internet, okay, for the enterprise WAN routers that lead to the internet, partner employees and guests, okay, with a grid like this table, okay. To link this security feature back to a packet forwarding consider when a new endpoint tries to send its first packet to a new destination. Here you can see the grid. Look at here. Between the employee and employee, this is not applicable. Between the internet and employee, the communication is permitted. Between the partner group and employee, the communication is permitted. Between the guest and employee group, the communication is denied. Again, between the internet and employee, it's permitted, and so on. Okay, what does it mean? Only you need to define some scalable group tags, okay, or SGTs, for example, employee, internet, partner, guest. And then you are completing this grid about the permit and deny communication between them, and automatically we will see that this happens in the network. Okay, let me to show you the VXLAN header with source and destination SGTs and VNIDs revealed to better understand the functionality of the SGT. The ingress SDA node starts a process by sending message to DNA center. DNA center then works with security tools in the network like Cisco Identity Service Engine or ICE to identify the users and then match them to their respective SGTs. Okay, actually DNA center then checks the logic similar to this table. Okay, if DNA center sees a permit action between the source and destination pair of SGTs, DNA center direct the edge node to create the VXLAN tunnel. If the security policies state that the two SGTs should not be allowed to communicate, DNA center does not direct the fabric to create the tunnel and the packet do not flow. You know that when we receive a packet in one fabric edge node, okay, we should ask from the control plane for receiving the destination outlook. Also, you know that we should receive some other information for VXLAN from the DNA center. Okay, in DNA center we have this table. According to this table, if the communication between the source and destination is permitted, we will receive the required information from the DNA center. But if we don't have the we don't have for example permit for communication, we won't receive the information that we need for encapsulating the packet with the VXLAN. Okay, this figure gives a brief insight into why SDA goes to the trouble of using VXLAN encapsulation for its data plane rather than performing traditional layer 2 switching or layer 3 routing. The VXLAN header has great flexibility, okay, in this case used to define both a source and destination SGTs, matching SDA's desired logic of allowing a subset of source and destination SGTs in the SDA fabric. The operational model with a scalable group greatly simplifies security configuration and ongoing maintenance of the security policy while focusing on the real goal, controlling access based on user. Okay, it means that only you need to change the rule between the employee and internet, for example, from permit to deny. You will receive different behavior of, in the, for example, SDA access, and you don't need to configure any accesses. Here, I'm not going to explain all of the detail of for example, this process. Actually, only I'm going to say that you configure this table, and with the help of a scalable group tag and availability of them in the VXLAN header, we can implement our security policy without the need to think about the IP addressing or some other things. Okay, actually we can say the operational model with a scalable group greatly simplifies security configuration and ongoing maintenance of the security policy while focusing on the real goal, controlling access based on user. From a controller perspective, the fact that Cisco DNA Center acts as much more than a management platform and instead as a controller of the activities in the network makes for a much more powerful set of features and capabilities. Alright, now let me to explain about the DNA Center as a network management platform. First, I will explain about the Cisco Prime Infrastructure or PI, and after that I will discuss about I will explain about the DNA Center as a network management platform. You know that The Cisco PI is one of the most powerful network management platforms in for many years that is released from the Cisco system. Cisco Prime Infrastructure has been Cisco's primary network management product for the enterprise. It includes the following features. First, single pane of glass. It means that it provides one graphical user interface from which to launch, okay, all PI or prime infrastructure functions and features. Also, the next feature is discovery, inventory, and topology. It means that it discovers network devices, build an inventory, and arrange them in a topology map. Also, we have enterprise or entire enterprise in the PI, provides support for traditional enterprise LAN, WAN, and data center management function. Methods and protocols uses SNMP, SSH, Telnet, as well as CDP and LLDP to discover and learn information about the devices in the network. Lifecycle management support different tasks to install a new device day 0, configure it to be working in production day 1, and perform ongoing monitoring and make change day n. Okay, application visibility simplifies QoS configuration deployment to each device. Converged wired and wireless, it means that enables you to manage both the wired and wireless LAN from the same management platform. Also, software image management or SWIM manage software images on network devices and automates updates. Okay, and also plug and play, perform initial installation tasks for new network devices after you physically install the new device, connect a network cable and power on. Actually, Prime Infrastructure or PI itself runs as an application on a server platform with graphical user interface access via a web browser. The Prime Infrastructure server can be purchased from Cisco as a software package to be installed and run on your server or as a physical appliance. Okay, this is the Prime Infrastructure. Only here I reviewed the Prime Infrastructure. You know that here I'm not going to explain about the detail of Prime Infrastructure. Now we can talk about the DNA Center and we will find some similarities with traditional management. About the Cisco DNA Center, if you read the user's guide for DNA Center and look through all the features, you will find all the features just listed here as traditional management features. For instance, both can discover network devices and create a network topology map. Human operators, rather than automated processes, often start with the topology map, expecting notices, flashing lights, red colors to denote issues in the network. As an example, in this figure, we can see a topology map from DNA Center. Both Prime Infrastructure and DNA Center can perform a discover process to find all the devices in the network and then build topology map to show the devices. Interestingly, DNA Center can work with Prime Infrastructure using the data discovered by Prime Infrastructure rather than performing the discovery work again. The graphical user interface mechanisms are relatively intuitive with the ability to click into additional or less for example, detail. Here in the right figure, a little more detail after hovering over and clicking on one of the nodes in the topology is available, and typical action and result in many management platform that you can use them. Okay. Also, don't forget we have many similarities between the PI and DNA Center about the network management platform, but you know that DNA Center, okay, has more capability from the, for example, a simple network management platform. You know that DNA Center is a controller, and we can use this controller as a simple network management platform or as a controller of the SD access. Also, we have some differences between the DNA Center and a traditional, for example, management. In a broad sense, there are several fundamental differences between the Cisco DNA Center and traditional network management platform like the Cisco Prime Infrastructure. The largest difference is that, as I mentioned before, Cisco DNA Center supports software-defined access, whereas other management applications do not. At the same time, given its long history as a of the time that now we are working with the Cisco DNA Center, Cisco PI or Prime Infrastructure still had some traditional management features not found in the Cisco DNA Center. So think of PI or Prime Infrastructure as comprehensive to traditional device management, with Cisco DNA Center having many of those features while focusing on feature or future feature like the SDA support. Okay, in terms of intent and strategy, Cisco focuses their development of Cisco DNA Center features towards simplifying the work done by enterprises, with resulting reduced cost and much faster deployment of changes. Cisco DNA Center features help make initial installation easier, simplify the work to implement features that traditionally have challenging configuration like ACL, and use tools to help you notice issues more quickly. Some of the features unique to Cisco DNA Center include the easy quality of service or easy QoS. It can help us to deploy QoS, one of the most complicated features to configure manually, okay, with just a few simple choice from Cisco DNA Center. After that, encrypted traffic analysis enables Cisco DNA to use algorithms to recognize security threats even in encrypted traffic. Device 360 and Client 360 gives a comprehensive 360-degree view of the health of the device. Network time travel shows past client performance, okay, in a timeline for comparison to current behavior. And path trace discovers the actual path packets would take from source to destination based on current forwarding tables. In the next video, I will explain about some of these features. Just to expound on one feature as an example, Cisco DNA Center's path trace feature goes far beyond the traditional management application. A typical network management application might show a map of the network and let you click through to find the configuration on each device, including ACLs. The path trace feature goes much further. The DNA user from the graphical user interface or the application programming interface specifies a source and destination host and optionally transport protocol and ports. Then the path trace feature shows a map of the path through the network and shows which ACLs are in the path and whether they would permit or deny the packet. All of Cisco digital network architecture sets about to help customers reach some big goals: reduced costs, reduced risks, better security and compliance, faster deployment of service through automation and simplified processes, and the list goes on. Cisco DNA Center plays an important role with all the functions available through its robust northbound API and with its intent-based networking approach for software-defined access. Cisco DNA Center represents the future of network management for Cisco enterprises.